Welcome to the video lecture on the chain rule. We already know how to differentiate a lot of functions, things like y equals x squared plus 1, but we don't know how to differentiate things like 1 plus x squared quantity cubed, 1 plus x squared to the 59th, square root of 1 plus x squared, and sine of x squared plus 1. Now for some of these, like 1 plus x squared cubed, we could expand that out by foiling and then take the derivative of each term. But as these powers get really large, like the 59th power, that becomes too tedious and time consuming to do. And for things like the square root or the sine function, that would be impossible to do. So what we're going to learn today is a very important rule called the chain rule. It's probably the most important rule that we'll use that enables us to take the derivative of functions like these that are sort of functions nested inside of other functions. Okay, so we're going to start with one version of the chain rule called the extended power rule. And this is finding the derivative of a function f of x that's being raised to some outermost power. So what would be the derivative of a function being raised to an outermost power? And this is what this chain rule says. You take the derivative of the outermost power first. So something raised to the nth would be bring down that power n and subtract 1 from the power. That's our power rule, right? So we're going to do that for this as well, but what's inside will stay that original function f of x, and then here's the new piece. We're going to multiply this by the derivative of that inner function, so f prime of x or df dx, however you want to write it. So it's kind of like we're peeling off the layers. We're going to take the derivative of that outer function first, leaving the inside function the same, and then we're going to multiply that answer by the derivative of that inner function. So suppose I have y equals 1 plus x squared quantity cubed. My outermost function is that cube. So the derivative is going to be the derivative of that cube first. And the derivative of a cube means bring down the cube, bring down the 3, subtract 1 from the power. What's inside needs to stay the same function that we had originally. And then we're going to multiply this by the derivative of that inside function. The derivative of 1 goes to 0. The derivative of x squared is just 2x. So we get y prime equals, and let's simplify this a little bit, 3 times 2x would be 6x times 1 plus x squared quantity squared. Okay? So what's going to change if I have x squared plus 1 raised to the 59? Now my outermost function is that 59. So to take the derivative of that, I would bring down the 59 and subtract 1 from the power. So the new power will be 58. What's inside stays inside. So x squared plus 1 stays the same. And then we need to multiply this by the derivative of that inner function. So the derivative of that would just be 2x. So make sure that you're taking the derivative of each piece of this function and just multiplying the results together. If we simplify here, 59 times 2 is 118x times that x squared plus 1 to the 58. So how do we handle a square root? Well, we're going to change it into a power first. We know that a square root is the same as 1 plus x squared raised to the 1/2. So now my outermost function is just a 1/2 power. So y prime will be the derivative of that 1/2. So you bring down the 1/2, and then you subtract 1 from the power, which makes it a negative 1/2. What's inside stays inside. And then you multiply this by the derivative of that inner function, which is that 2x again. When I go to clean this up, the 1/2 and the 2 cancel out, so we just get x times 1 plus x squared to the negative 1/2. And if you want, you can leave the x where it is and flip that 1 plus x squared to the denominator and put a square root around it, just to kind of clean it up a little bit. Okay? All right, the next example here is a little bit more complicated. Here we have x plus 1 cubed times 3x minus 4 to the fourth. Now, the x plus 1 cubed is like a chain rule because it has that outer function and this inner function. And then the fourth power is like an outer function and we have another inner function. So we have chain rules going on for both of these pieces. But what is sometimes overlooked here is the fact that these two functions are being multiplied together. So this is really a product rule, first and foremost. We need to take the derivative of this product, and then within that, we're going to be using chain rules as well. So it's a kind of combination of a couple of rules. So let's start with our product rule. The reason I want that product rule is because I have a first function times a second function. So the way the product rule works is you would do the first function unchanged, so x plus 1 cubed, times the derivative of this second function. And that's where the chain rule comes in, because the derivative of this second function is going to be the derivative of that outer function 4. So you bring down the 4 and you subtract 1 from the power, which makes it a 3, and then what's inside stays inside times the derivative of what's inside. Now what's the derivative of 3? 0. What's the derivative of a minus x? Negative 1. Don't forget that negative 1. Okay? So we did first times derivative of second. Now we need to do second, which is this 3 minus x to the fourth, times the derivative of the first. And that's because of our product rule. So the derivative of the first, right here, has an outer function 3. So we bring down the 3, subtract 1 from the power, what's inside stays inside, times the derivative of the inner function. And the derivative of x plus 1 is just a 1. So we have first times derivative of the second plus second times the derivative of the first. Now I want to show you how the easiest way to clean this up. This is something that you'll see quite often, so you'll want to learn this technique. The trick that we're going to use here is we're just going to do some factoring. If you think of all of this to the left of the plus sign as one big term, and all of this to the right of the plus sign as a second term, what do they both have in common that I could factor out? Well, they both have some x plus 1's, and they both have some 3 minus x's. How many of each can I pull out? You always want to take the smaller of the two powers. So if I look at those x plus 1's, I have 3 here, but I only have 2 here. So I can only pull out 2 at most. Then if I look at my 3 minus x's, I have 3 here and I have 4 here. So again, taking out the smaller of the two powers, the most I could pull out would be 3. Then what we're going to do is in brackets, we're going to write down what would be left over. So I took out all 3 of those. So what's left is this 4 times that negative 1, which is a negative 4. And then I only took out 2 of these, so there should be 1 left. Use parentheses because it needs to get multiplied by that negative 4 out front. Now I write my plus sign and I move to this second box. Again, I pulled out all of these x plus 1 squareds, so I have a 3 times a 1 left, would just be 3. And I only pulled out 3 of these, so there's still 1 of these 3 minus x's left as well. And now what I'm going to do to clean it up is just go ahead and leave these first 2 factors alone. Don't bother distributing them or foiling them out. Just leave them in that factored form. But I am going to go ahead and distribute inside these brackets because I see that I'm probably going to have some like terms that can be combined. So I'll have a minus 4x and a minus 4 plus 9 minus 3x. And when I simplify there, negative 4x minus 3x is negative 7x. Minus 4 plus 9 is 5. And again, I'm just going to bring down my x plus 1 squared and my 3 minus x cubed, and here is my final answer. So when you have a product rule like this, usually you're going to want to do some factoring to help you clean it up and get a nice answer. Okay, let's look at the next example. We have y equals the cube root of x plus 1 over x minus 2. So in order to attempt this problem, first thing you want to probably do is change that cube root to an outermost power. So I'm going to change it to parentheses and then raise all of this stuff in parentheses to the 1/3 power. Now this is ideal for our chain rule because we have an outermost function and then we have this complicated inner function as well. So we're going to start with this outer function first and take its derivative first. So the derivative of something to the 1/3 is a power rule. You bring down the power, bring down the 1/3, and then you subtract 1 from the power. 1/3 minus 1 would be negative 2/3, so that's my new power. What's inside needs to stay inside, unchanged. So far all I've done is the derivative of that cube root, but I haven't done the derivative of the inside function at all yet, so that's what's next. And you're always going to multiply these pieces together. So I'm going to multiply by this derivative of this quotient right here, which means I need to use a quotient rule. So this has both a chain rule in it and a quotient rule as well. So remember how your quotient rule goes. It's low d high minus high d low over low low. So we're going to do low, which is that x minus 2, times d high. The derivative of this top would just be 1, minus high, which is that x plus 1, times d low. The derivative of x minus 2 is just a 1, over low low, or the bottom squared. Okay, notice I'm completely ignoring this 1/3 power when I do my quotient rule because I already did that. I did that over here. So we're just doing our quotient rule on this inside stuff. Now let's go ahead and clean up our numerator over here. I'm going to get an x minus a 2, and then when I distribute my negative, I'm going to get a minus x minus 1. So when I cancel out my x's, I'm going to get a negative 3 over x minus 2 quantity squared times that 1/3. So this 3 and this 1/3 can cancel, and my final answer will be negative 1 over that x minus 2 squared, and then I have that x plus 1 over x minus 2 to the negative 2/3. And there's obviously different degrees of simplifying there. You can flip this fraction around and make that power positive. You can throw in your cube root and your square. You can do lots of things with it, but I'm just going to stop right here for now. Okay? Now if we look at this last one on this page, we have y equals negative 2 over 4 minus x quantity cubed. Now if we want to make this much easier for ourselves, the best thing to realize, so that you don't have to use that yucky quotient rule again, is to realize you can take this entire quantity and move it up to the top. So this function becomes negative 2 parentheses 4x minus 3 to the negative 3rd power. And now I still need a chain rule because I have an outer function here and a complicated function on the inside as well. There's two functions nested within each other. So the way the chain rule works is we would take the derivative of that outer power first. Well, don't forget you have this negative 2, and that's just a constant multiplier. So the negative 2 is going to stay put, and when I take the derivative of that negative 3 power, you bring the power down and you subtract 1 from the power, so the new power would be a negative 4, and what's inside stays the same. So now I've done the derivative of that power, but I still need to multiply this by the derivative of this inside part. And the derivative of 4x minus 3 is just a 4. So when we clean this up, negative 2 times negative 3 is 6. 6 times 4 is 24. And you can take that negative power and make it positive by flipping this 4x minus 3 back down to your denominator. So here's my final derivative. Okay? So the chain rule that we've seen so far is for an extended power rule. When you have an outermost power, you bring down the power and subtract 1 from the power, and then you multiply that by the derivative of what's inside. What I'm going to write out now is the more generalized chain rule, and this works for any kind of problem that has 2 or more functions nested within each other. And when you have functions nested within each other, that's actually called a composition of functions. So it would look like an outer function f with an inner function g inside of it. So this is your outer, and this would be your inner function. And what we're going to do is want to know how to take the derivative of something that looks like that. So what we're going to do, according to the chain rule, is you start with your outer function first. So we're going to take the derivative f prime of that outer function. And we're going to evaluate it at the same inner function that I had originally, g of x. And then I'm going to multiply this by the derivative of the inner function, which in this case is that g. So the derivative of g would be g prime. So you start on the outside and you take derivatives as you go. So you start by taking the derivative of the outer function, f prime, and then you multiply that by the derivative of g prime. So you get f prime of g of x times g prime of x. And we're going to practice this a lot, but before we do, I'm going to show you one more alternative form of the chain rule. So instead of writing your function in this notation, f of g of x, sometimes you will occasionally see a new variable created. Sometimes you'll see problems where you let y be a function of u, and then you let u be this g of x. So if you think about that for a moment, what would that be the same as? Since u is g of x, then I could take that g of x and substitute it in for that u. So y is really just f of g of x. So it's really the same kind of situation that we started with up here, but it's just created a new variable to help break up our function a little bit. Now, if you have it in this notation where you have this new variable u involved in your problem, then the chain rule would still apply, but this is what it would look like. The derivative of the function y with respect to x turns out to be the derivative of the function y with respect to this u, this sort of intermediate variable, times the derivative of u with respect to x. These du's on the top and the bottom here kind of cancel each other out, which is why we're getting that dy over dx. Okay, so it's kind of funny to see it in this form, but let's try out an example so you can see what I mean. So suppose that you have y equals square root of u, and u is defined to be 1 minus x squared. So just so you notice here, y is really the square root of u, but since u is 1 minus x squared, that means y is really square root of 1 minus x squared. So we would know how to take the derivative of this using our extended power rule, because you could think of this as 1 minus x squared to the 1/2, and therefore the derivative would be taking the derivative of that 1/2 power first by bringing the 1/2 down, subtracting 1 from the power, what's inside stays inside, and then multiplying this by the derivative of that inside function, which would be a minus 2x. And then the 1/2 and the 2 would cancel, so this is really like a negative x over square root of 1 minus x squared. So that's how we would probably normally do this problem. But if for some reason they gave this problem to you in terms of this intermediate variable u, here's how you could use that alternative form of the chain rule as well. So here's how it works. If I want dy dx, otherwise known as y prime, then what I could do is find the derivative of y with respect to u first, and then multiply that by the derivative of u with respect to x. So let's find dy du. Well, y is square root of u, or u to the 1/2 power. So what would be the derivative of this u to the 1/2 with respect to u? What's the derivative of that y with respect to u? Well, the derivative of u to the 1/2 would be 1/2 u to the negative 1/2, just using our power rule on u to the 1/2. Okay, so that's what dy du is. Now we're going to multiply this by du dx. So you go to your second function over here, and if u is 1 minus x squared, then the derivative of this u function with respect to x would just be the derivative of 1 minus x squared with respect to x. And that, we know, is just negative 2x. Okay, so here's what our derivative is looking like. This is our y prime. The 1/2 and the 2 cancel out, but we have a slight problem. We have a u multiplied by an x, and we don't really want to have two different variables here. So what could we do? Well, we know what u is in terms of x. What we can say is, since u is 1 minus x squared, let's substitute in 1 minus x squared right there for that u. So this becomes 1 minus x squared to the negative 1/2, and it was being multiplied by this other negative x. And if we clean that up, that becomes a negative x on top, and when I flip this guy down and put in a square root again, we get that square root of 1 minus x squared on the bottom, which is exactly the answer we would have gotten doing it this route instead. But I wanted to show you one of these kinds of problems where you use that dy dx equals dy du times du dx. Basically, we're just taking the derivative of the first function and multiplying it by the derivative of the second function, and then you might have to substitute in your variable at the end to put it all in terms of x. Okay? All right, let's try some trig examples, and these are pretty common uses of the chain rule. Here we have y equals sine of x squared plus 1. So this is a chain rule because your outermost function is this sine function, and all of this is your innermost function. So the way the chain rule works is y prime is going to be the derivative of this outer function first. What is the derivative of sine? It's cosine. And this is going to be cosine of the same stuff that I had originally, so that won't change. So now I've done the derivative of the sine function, but I haven't done the derivative of this inner function. The derivative of the inner function would just be a 2x, and these two derivatives always get multiplied together by the chain rule. So here's what my answer will be. If you want, you could put that 2x in front, and this becomes 2x cosine of x squared plus 1. And there's our derivative. Okay? All right, let's try that again over here. We want the derivative of sine of pi x. This is like sine of, and you can use parentheses here to reinforce the fact that you have an outer function, which is the sine, and then you have an inner function, which is that pi x. So you have to use your chain rule here. You're going to start by taking the derivative of the outer function sine first, and the derivative of sine is cosine. And it's going to be cosine of the same thing that I had originally here. So cosine of that pi x. But I need to multiply this still by the derivative of this inner function. And what's the derivative of pi x? Well, that's like the derivative of 3x. 3x would go to 3, so the derivative of pi x goes to pi. That pi is just a constant. So just rewriting this, I'm going to put that pi in front, and this becomes pi cosine of pi x. Okay? All right, next example, secant of x squared. Now I want you to notice here that there's no parentheses. So this is not the same as secant of x quantity squared. Okay? In this problem, it's just the x that's being squared. So you want to think of it this way instead. So my outermost function is that secant, my innermost function is that x squared. So the derivative would start with the derivative of secant. And you need to have that memorized. Remember, the derivative of secant is secant times tangent. So this is going to be secant of the same thing that I had originally, x squared, times tangent of that same x squared. You don't want to just write sec tan. It needs to be secant of something and tangent of something. And that something should be the same argument that I had originally right here. Now, all I've done so far is done the derivative of that secant. We still haven't done the derivative of this x squared, which we know goes to 2x. So now that's done. We multiply the two pieces together. So this is 2x secant x squared tangent x squared. And there's our derivative. All right, now this next one, be careful. Notice that square is sort of in between our sine and our 3x. That is just a shorthand notation for saying sine of 3x quantity squared. You need to know that that's what that means. So your outermost function isn't the sine. Your outermost function is the square. So that's where you want to begin. So our derivative of a square, you bring down the 2 and you subtract 1 from the power. What's inside should be that sine of 3x. Now the next innermost function would be the sine. So what's the derivative of sine? Cosine. And it needs to be cosine of something. And that's going to be the same thing that we had the sine of. And this was sine of 3x. So this should be cosine of 3x. So we've done the square. We've done the sine. We still haven't done the 3x. What's the derivative of 3x? Just a 3. And that needs to get multiplied. All of these pieces get multiplied together by the chain rule. So when I combine it, 2 times 3 is 6. So this is 6 sine 3x cosine 3x. Okay? Next example. Sine of cosine of x. So our outermost function is this sine. That's where you want to start. So the derivative of that sine is cosine, and it's cosine of the same thing that I was taking the sine of. And I was taking the sine of cosine of x. So you should be getting cosine of cosine x. Now we're not done. That was just the derivative of this piece. Now we need to do the derivative of this piece. What's the derivative of cosine x? You need to have this memorized. Remember, derivative of cosine is minus sine of x. And the derivative of that x is just a 1, so that's not going to contribute anything towards my derivative. So simplifying, I'm going to pull that negative all the way out front. I'm going to pull that sine x all the way out front, and then I have my cosine of cosine x. And there's my final answer. All right, the last one here has that little square. So you want to recognize that this is really the same as sine of cosine of x quantity squared. So it's the cosine that's being squared. So think about your order here. What is the outermost function? Is it the square, is it the sine, or is it the cosine? It's actually the sine, because we are taking the sine of this quantity squared. So you have to get past the sine first before you can square anything. So it's this sine that you want to start with. So our derivative will be the derivative of that sine, which is cosine, and it's going to be cosine of all of this stuff. So cosine of x squared. Now that this sine is gone, what's our outermost function? Our next outermost function is the square. So the derivative of a square would be bring down the 2, subtract 1 from the power, and what's inside stays the same. So now we've done the square. Finally, the innermost function now is the cosine of x. What's the derivative of cosine x? Negative sine x. So let's clean it all up. I'm going to take this 2 and this negative and put it out front. And then I have this sine x and this cosine x. And then I have all of this cosine squared. Whoops, I put that 2 in the wrong place, sorry. Cosine of cosine squared x. You can leave it out like I did here, or you can put it in like I did there. Either way is correct. Okay? All right, we've learned our chain rule. Now what we're going to do is learn how to apply the chain rule to derivatives of exponential and logarithmic functions. So let's start with a definition of a derivative rule that we've already learned. The derivative of e to the x we know is e to the x right back again. So what we're going to do is we're going to expand this into our chain rule idea. What if instead of having just e to the x, you have e to the stuff, something more complicated than an x? That's what this u is right here. It's a function of x. It could be an x squared, it could be a tangent of x, it could be anything at all. So according to the chain rule, the derivative of this is going to be that e to the u right back again times the derivative of that u with respect to x. So this is e to the u times du dx, or e to the u times u prime. Now I like to teach my students this sort of layman's notation. Suppose we think of this as e to the stuff. Then the derivative of e to the stuff, or e to the u, is e to the stuff right back again times stuff prime, the derivative of that stuff. That's what this really means right here. So e to the stuff, you always get back that same e to the stuff, but then you multiply it by stuff prime. So let's try that on this next example. So the derivative of e to the x squared minus 3x plus 1. All of this is my stuff. So the derivative will always be e to the stuff right back again. You're basically just recopying the original problem. But then we're going to multiply that by the derivative of all that stuff. And the derivative of x squared would be 2x, and the derivative of minus 3x plus 1 would just be minus 3. I'm going to wrap that in parentheses, or you can take that 2x minus 3 in parentheses and put it out front. Either way is correct. So there's my derivative. Okay, so let's try it on this one. I have 2e to the 1 over x. So this 1 over x is my stuff. Now, I don't like thinking of this as a 1 over x because that would require using a quotient rule to take the derivative of 1 over x. So instead, let's think of this function as 2e to the x to the negative 1. I'm basically just moving that x up to the numerator. And now let's take the derivative of that. So first, think about that 2 for a moment. 2 is a constant multiplier, so it will stay there, and then this becomes e to the stuff, where my stuff is that x to the negative 1. So the derivative of e to the stuff is e to the stuff back again times the derivative of this stuff. And what's the derivative of x to the negative 1? Well, you bring down the power, and then you subtract 1 from the power. So it becomes negative 1x to the negative 2. Cleaning this up, 2 times negative 1 is negative 2. This x to the negative 2 can be moved to the bottom and be made into an x squared. And then this e is on top. If you want, you can change this x to the negative 1 back into a 1 over x. So cleaned up, nice and neat, it would look like negative 2 e to the 1 over x all over x squared. All right, let's try this one. The derivative of 1 over e to the x. Again, this is essentially a quotient rule if you just started right away and jumped right in, because you have one great big fraction. If you want to avoid the quotient rule, you can take this e to the x and move it up to the top, and that changes that exponent to a negative. So instead what I'm going to do is think of this as e to the negative x instead. And then I don't have to use my quotient rule at all. This is e to the stuff because it's not just a plain old x up there, it's a negative x. So to do the derivative correctly, you recopy the original problem. So there's my e to the stuff, back again, times the derivative of this stuff. Well, what's the derivative of negative x? It's just a negative 1. So if you want, you don't have to, but if you want, you can move this e to the negative x back to the denominator so that negative 1 would stay on top, and then this e to the x now goes to the bottom. So there would be my answer. All right, the last one here, the derivative of e to the x. So the bottommost e is my base e, and that means this e to the x is my stuff. So according to my rule, I'm going to do e to the stuff back again, so just basically recopying the original problem, times the derivative of this stuff. What's the derivative of e to the x? E to the x right back again. So here's my final answer. E to the x times e to the x. If you wanted to, just so you know, since these share a common base of e, you are allowed to add those exponents. So this could be written as e to the x plus x. And there's our answer. Okay, now let's move to logarithmic functions. So now we're going to take the derivative of ln of x. Now we're going to prove this in just a moment, but the derivative of ln of x is going to be defined to be 1 over that x. This x is called the argument of our logarithm. So the derivative of ln of x is just 1 over that x. Now what if you have something more complicated than just an x? What if it's a function of x like a u? Then the chain rule says that the derivative will be 1 over that u, just like we had 1 over that x, but then you multiply that by the derivative of whatever that u is. So u prime over u, or 1 over u times du dx. Now if you like my layman's terms, then this is what it would look like. The derivative of ln of stuff can be thought of in two different ways. It's 1 over that stuff times stuff prime. That's what this notation is right here. 1 over that argument times the derivative of that argument. Or if you wanted to just consolidate these into one single fraction, that's stuff prime on top over stuff on the bottom, and that's what this notation is right here. So a lot of times I'll just say the derivative of ln of stuff is stuff prime over stuff. Okay, so we'll practice this in a moment, but let's prove that the derivative of ln of x is 1 over x first. So the way I'm going to start my proof is I'm going to let y be defined to be the ln of x, and I want to know what is dy dx. That's what I'm trying to figure out. What is the derivative of this function? Now in order to figure that out, I'm going to rewrite this using the equivalent exponential form. Remember, an ln is a base e. So this y equals ln of x statement is the same as e to the y is equal to x. These are equivalent because of the inverse relationship between logs and exponentials. The reason I'm going to think of it in this way is because I have derivative rules for exponentials. So I'm going to take the derivative of this statement right here. So I'm going to take the derivative with respect to x of e to the y, and that should equal the derivative with respect to x of the right side. So let's do that. What's the derivative of e to the y? Well, this is like e to the stuff. So the derivative of e to the stuff is e to the stuff right back again times stuff prime. Well, what's the derivative of y? Well, we just call that dy dx, or you could write y prime right there. So this is my e to the stuff times stuff prime. What's the derivative of x with respect to x? Well, that just goes to 1 because these x's match, these variables match. So how would I solve this for dy dx? Remember, that's what I was trying to do. I wanted to know what dy dx was. I wanted to know what the derivative was. So let's divide by this e to the y, and that means dy dx is equal to 1 over e to the y. And remember back up here what e to the y was equivalent to? E to the y is the same as x. So this is the same as 1 over x. So we've just proven that if y is ln of x, then the derivative of y is 1 over x. So we've just proven that derivative rule for logs. All right, let's try it. So what would be the derivative of ln of 5x? Well, according to our rule, this is ln of stuff, where my stuff is this 5x part. So you can think of this a couple of different ways. You can think of this derivative as 1 over that stuff times stuff prime. Well, what would be the derivative of 5x? Just a 5. If you consolidate this, that's like stuff prime over stuff, just moving that 5 over. And you'll see that those 5's cancel, so this turns out to be 1 over x. Okay? Let's try this example over here. We have the ln of the square root of 2x minus 1. So let's find the derivative of it. I'm going to show you this derivative in two different ways. So the first way is going to be just jumping right in. Now, when I see this, I see that ln, that's kind of my outermost function. Then I see a square root, which is my next function, and then I see 2x minus 1, which is like my third function. So when I take my derivative, I'm going to have three pieces, three different derivatives, one for each function, and I'm going to multiply all of those together. Now, in order to deal with the square root, it's probably a good idea to change that square root to a power. So I'm going to replace the square root with parentheses and raise the parentheses to the 1/2. So now let's jump in. Our outermost function was that ln. So the derivative would be the derivative of that ln, which according to our rule, if it's ln of stuff, you're going to take 1 over this stuff. So 1 over this argument, 2x minus 1 to the 1/2. And then we have to multiply that by the derivative of this stuff. So the ln is now done, and I move on into the inside. Now this has two functions within it as well. The outermost one is that 1/2 power. So what's the derivative of a 1/2 power? Well, you bring the 1/2 down, and you subtract 1 from the power. So 1/2 minus 1 would be a negative 1/2, and what's inside stays inside. So now we've done the derivative of the 1/2. Finally, we move inside those parentheses. What's the derivative of 2x minus 1? That would just be 2. And the chain rule says I multiply these three different derivatives together. So here's what I have so far. Now let's clean it up. The 1/2 and the 2 cancel out. If I take this negative 1/2 power and move it down to the denominator and turn it into a positive 1/2 power, these two things in parentheses match. So these have the same base. So I get to add these powers. And a 1/2 plus a 1/2 is just a 1. So this becomes 2x minus 1 raised to the first power, or just 1 over 2x minus 1. So there's my derivative. Okay? So that's one way to do this problem. Now I want to show you another way to do this problem, and that is to use some properties of logs. So remember how we had this function and we changed it so that instead of having a square root, we had that 2x minus 1 to the 1/2 power. Well, that is very similar to the ln of a raised to a b, an expression raised to a power. And we have a property of logs that says if you have ln of something raised to a power, you get to move that power down out front. So this could be rewritten as b times the ln of a. This is called the power property for logarithms. So that's what I'm going to do here. I'm going to take this 1/2 and I'm going to move it down out front. So this becomes 1/2 ln of 2x minus 1. So now instead of having to deal with that square root, it's turned into a constant multiplier. So if this is my function, I haven't done any derivatives yet, but if this is my function, then the derivative of it would be this constant multiplier stays put, and then I multiply it by the derivative of this ln of stuff. This is my stuff, so the derivative of ln of stuff is 1 over that stuff times stuff prime, and the derivative of 2x minus 1 is just 2. So the 1/2 and the 2 cancel, and we get 1 over 2x minus 1. Same answer that I got over here, but I avoided having to deal with any of those fractional powers. So using properties of logs can really make these ln derivatives a lot simpler to do. Let's try a couple more examples like that. So this next example is kind of a yucky one because you have ln of 2x times x plus 1 cubed all over the cube root of 2x squared plus 1. And in order to take the derivative of this, our outermost function would be that ln, and then all of this crazy stuff inside is my inner function. And involved in all of that, there's a product on top, there's this big quotient on the bottom, and then we've got these outer powers as well, so there's a chain rule involved also. So we've got product rules, quotient rules, and chain rules involved. So that's a lot of work. So instead, what I'm going to do is I'm going to employ some of my properties of logs. I'm going to use properties of logs to help me simplify this first. So let me remind you a couple of laws that we're going to use. One law that we're going to do is the ln of a product. So something like the ln of a times b. The ln of a product becomes a sum of two logs. So this becomes ln of the a plus ln of the b. Similarly, ln of a quotient, a divided by b, becomes the difference of the logs. So ln of the a minus ln of the b. And then we're going to use that power property again. Ln of a to the b becomes b times ln of a. So these are the three properties that you want to use in a problem like this. So let's start. We're not doing any derivatives yet. We're just going to break down this function right here into a bunch of pieces. So the first thing I'm going to do is I'm going to take the quotient rule here. I have this as my a and this as my b. So that becomes ln of that a, or ln of that whole numerator, minus ln of that b. Now within the numerator, there's a product. So this is like my a, and this is like my b. So this becomes the ln of this, or the sum of the ln's. So ln of the 2x plus ln of the x plus 1 cubed. And then finally, I have some powers. I have a cube, which I'm going to bring out front, and I have this cube root, which I'm going to bring out front by thinking of it as a 1/3 power. So this becomes ln of 2x plus 3 ln of x plus 1 minus 1/3 ln of 2x squared plus 1. Okay, now you could, if you wanted to, break up this product 2 times x into ln of 2 plus ln of x. That would work fine. I'm just going to leave it as is because it's fairly simple to deal with right now. Now notice that we haven't done a single derivative yet. All we've done so far is break up our big quotient and turn it into a sum or difference of a bunch of logs. But the derivative of this whole big function that we started with should equal the derivative of all these little pieces. And hopefully these little pieces are going to have much simpler derivatives. So what we're going to do first is take the ln of 2x and find its derivative. So this is ln of stuff, so its derivative will be stuff prime over stuff. So this is the stuff that always goes in your denominator. The derivative of that goes in your numerator. So these 2's are going to cancel, and we're just going to get a 1 over x. So that was pretty easy. Now we go to the next one. The 3 is a constant multiplier, so it stays there. This is my stuff. So in the derivative, that stuff always goes in the denominator, and the stuff prime, which in this case is 1, goes in the numerator. So if I just consolidate that 3, put it on top, we get 3 over x plus 1. Again, that was really easy to do. And then this last piece, that 1/3 stays put because it's a constant multiplier. All of this is my stuff, so in the derivative, all of that goes to your denominator. And the stuff prime, or the derivative of this, would be 4x, and that goes in your numerator. So this becomes a minus 4x over, use parentheses because you want 3 times that whole denominator. And there is my final derivative. Not once did I have to use a product rule or a quotient rule. So it was a lot of time saving by using those properties of logs first. Okay, let's take a look at this next example. This is a pretty common example. We want the derivative of the ln of x. So our derivative is going to require realizing that I have two functions nested within each other. This ln is my outermost function, and then this ln is my innermost function. So according to the chain rule, this derivative will be the derivative of this ln first. Well, that ln has this for its stuff. So the derivative of that ln, that outer one, would be 1 over its stuff, and its stuff is ln of x, times the derivative of that stuff. Well, what's the derivative of this ln of x? Well, that's 1 over its stuff, and its stuff is just an x. And finally, the derivative of that x just goes to 1. So if I put it all together, I'm just going to rearrange the order in the denominator a little bit. I'm going to put the x first and then ln of x in the bottom. So the ln of x came from the derivative of the first ln, and the x in the bottom came from the derivative of the second ln. Okay, we've learned rules now for how to take the derivative of e to the stuff and ln of stuff. What we're going to talk about next is how to take derivatives of exponentials and logs that have bases other than e. So something like a to the x, so 2 to the x, 3 to the x, 5 to the x, or log base a of x, so log base 5 of x, log base 10 of x, something like that. So these a's are something other than e. And in order to do that, we're going to have to use a couple of properties to prove these derivative rules. It turns out that a to the x is the same as base e raised to the x ln a. And that's because ln is base e, so this base e and this base e cancel out, and you end up getting a to the x back again. This is one of those cancellation properties that you would have learned about when you're learning properties of logs in college algebra. Similarly, log base a of x can be rewritten with a base of e as well, using something called the change of base formula that you would have learned back when you learned about logarithms as well. And the way the change of base formula works is you can pick any base you want, but I'm going to use base e, which is an ln, because that's what I already have derivative rules for. So I'm going to change log base a to log base e, which is an ln. And to do that, you do ln of this x first over ln of the original base a on the bottom. So log base a of x is the same as ln of x over ln of a. So let's go ahead and see what some of these rules are going to be. So if we have the derivative of a to the x, where this a is something other than e, then the new rule is going to be you get that a to the x right back again, but this time you have to multiply it by the ln of that base a. So think about this for a moment. If this was e to the x, the derivative of e to the x is supposed to be e to the x right back again, and the ln of e is just a 1. So this rule still applies even if your base a is e. The only difference is if your base is not e, then you'll get this extra little constant, ln of a, being multiplied by your answer. So what if it's a to the stuff? Well, the same rule applies. If this was e to the stuff, we would have gotten e to the stuff times stuff prime. Well, that's still true, but now we're just going to multiply by that extra little constant ln of a. So a to the stuff is a to the stuff back again times stuff prime times that extra little ln of a. So let me prove this one to you before we talk about the log. So suppose I wanted to find the derivative with respect to x of a to the x. So in order to do this, I'm going to change a to the x into a base of e, and that's by using that cancellation property that we mentioned on the previous page. A to the x is the same as e to the x times ln of a. So I have rules for how to take the derivative of e to the stuff. According to this, this is my stuff. So the derivative of e to the stuff should be e to the stuff right back again times stuff prime. Well, this is like x times a constant. So the derivative of x times a constant would just be that constant, and this constant is that extra little ln of a that we have on the side. And then if you rewrite e to the x ln a back in terms of a to the x, you get this rule that we have right here. So we've just proven that the derivative of a to the x is a to the x right back again times ln of a. Okay, so it's very, very similar to the rule for e to the x. You just get an extra little constant multiplier. Now it's very, very similar for logs as well. So if you have a log base a of x, what would its derivative be? Well, think about what the derivative of ln of x is. The derivative of ln of x is just 1 over x. So we see that right here. But what we get is this extra little ln of a constant, but this time it's in the denominator instead of being up here in the numerator like we had for exponentials. So your derivative rule for log base a of x is 1 over x times that ln of a in your denominator. What would it be for ln of stuff? We know that that's 1 over stuff times stuff prime. That's still true here if the base is something other than e. So if you want the derivative of log base a of u, it's 1 over that u times u prime, and then you get that extra little constant on the side next to the denominator. Okay, so we're going to practice these, but let me prove this logarithm rule one last time for you. So what would be the derivative of log base a of x? What's this rule going to be? Well, in order to figure it out, we have to change this base a into base e, because the only laws or rules that we know so far are the ones for ln's. So this is where that change of base formula comes in. Log base a of x is defined to be ln of x over ln of a using that change of base property. If you want, you can think of that ln of a and pull it out front and think of it as just like a constant, because a is a number, so ln of a is a number. So 1 over ln of a is just a constant. And the only piece of this right here that's a function is the part with the x, the ln of x. So what would be the derivative of this? Well, the 1 over ln of a acts as a constant multiplier, so it's going to stay in our answer. And the derivative of the function part, the derivative of the ln of x, we know that that is just 1 over the x. So just rewriting this nice and neat, this is 1 over x times that extra little constant ln of a in the bottom. So the rules are exactly the same as they are for ln's, but you get an extra little constant multiplier in your denominator. Let's practice. Okay, so suppose we have the following function, y equals 3 to the x. So here my base is 3. So according to our rule, the derivative of this is going to be that 3 to the x right back again, but because the base is not an e, we have to multiply this by the constant ln of 3. And that's it. Okay, you get 3 to the x right back again times ln of 3. You just get that little extra constant on the side. Okay, so if this had been e to the x, we would have gotten e to the x right back again, and we wouldn't have gotten any extra constant. So that's the only difference when our base is something other than e. All right, let's try a log. Log base 5 of x squared. Now you have your choice here. You can leave it x squared, or if you want, you could pull that 2 out front. I prefer to pull the 2 out front just to make this x more simplified. So then to find y prime, the 2 is like a constant multiplier, and now I'm just trying to find the derivative of the log base 5 of x. So this is how it goes. If this was ln of x, the derivative of ln of x would have just been 1 over x. But because it's not an ln, but was base 5, we get an extra ln of 5 in the denominator. That's the only difference. So when I clean this up, I get 2 over x ln 5. And there's my derivative. Okay, what if I have 2 to the e to the x? So this is like 2 to the stuff, where the stuff is that e to the x. Okay, this is my stuff right here. So according to my rule, the derivative of 2 to the stuff is 2 to the stuff right back again times stuff prime. Well, what would be the derivative of e to the x? E to the x right back again. And then the one thing I'm missing here is the original problem was a base 2. So you need that extra little ln 2 multiplied next to everything else. So here would be my final derivative. 2 to the stuff times stuff prime times ln of 2. Okay? All right, the last one here, log base 3 of cosine 2x. So my outermost function is this log base 3. And all of this is my stuff. So according to my rule for y prime, this is going to be, just like for an ln, stuff prime over stuff. So all of this is my stuff that always goes in the denominator when you're taking the derivative of any kind of a log. Stuff prime goes on top. Now to do stuff prime requires another chain rule because you have an outer function and an inner function. What would be the derivative of the cosine piece? Well, the derivative of cosine is minus sine, and it should be minus sine of the same thing that I was taking the cosine of before, which was that 2x. So I've done the derivative of the log, I've done the derivative of the cosine, I still haven't multiplied this by the derivative of the 2x, which is a 2. And then I have one last little piece. Remember, this was a log base 3, not a log base e. So you're going to get that extra little multiplier, but because it's a log problem, it goes in the denominator. So you're going to get that extra little constant, that ln of 3, multiplied in the bottom. Now there's lots of ways to rewrite this. You could notice that sine 2x over cosine 2x is actually a tangent of 2x. You don't have to do that, but it's an option. And then I would have that minus in that 2 out front, and then an ln of 3 still in the bottom. Okay? All right, this last example here is a challenge question. So this is asking us to find the derivative of the ln of the square root of the ln of the ln of the cosine of x cubed minus 2x. So this is a big time chain rule problem because we've got all these functions nested inside of each other. The outermost ln is here. Then we have our square root, then we have an ln, another cosine, and then all of this stuff in the middle. So what the chain rule is going to say is that we would need to take the derivative of each one of these and multiply them all together. Now, one thing I could do to make my life just a tiny bit easier is to get rid of that square root by changing it to a power. So this would become ln of, I'm going to change it to parentheses. Everything inside stays the same. Close the parentheses on the x cubed, close the parentheses for the cosine, close the parentheses for the ln, and then that 1/2 goes on that second to first ln, okay? So we could change that square root to this outer power. So this is really looking like ln of stuff to the 1/2. And we can use our power property to take that 1/2 and bring it out front. So that's what I'm going to do. I'm going to take this 1/2 and I'm going to bring it out front and turn this into 1/2 ln of cosine of x cubed minus 2x. Okay, I think I have all my parentheses in there. Okay, so now what we're going to do is we're going to work our way from the outside in, taking derivatives as we go. So the derivative of this would become, first deal with that 1/2, that's a constant multiplier. So the derivative of that 1/2, the derivative with that 1/2, the 1/2 stays there, and we multiply it by the derivative of everything that's left. So starting from the outside and working in, the derivative of this ln is 1 over its stuff, and its stuff is all of that. So I want 1 over ln of cosine of x cubed minus 2x. Okay, so that means we're done with that ln. And now we're going to multiply it by its stuff prime, which is the rest of this. So that's another ln. So the derivative of this ln would be 1 over its stuff, and its stuff is all of this. So I want 1 over ln of cosine of x cubed minus 2x. And that's that ln taken care of. Now we move to the next ln. Its stuff is this cosine. So the derivative of ln of that black stuff is 1 over cosine x cubed minus 2x. So I've now done that ln. And then I move inside, and now I'm at the cosine. What's the derivative of cosine minus sine of the same stuff that I was taking the cosine of, so x cubed minus 2x. So now we've done the derivative of the cosine. And last but not least, we want the derivative of this cubic, which would be 3x squared minus 2 wrapped in parentheses. So I had 1, 2, 3, 4, 5 different functions, and I have 1, 2, 3, 4, 5 different derivatives, and they're all being multiplied together. I'm not going to bother simplifying it all, but this is what our chain rule would give me. This is the derivative of the very first ln. This blue part is the derivative of the second ln. This black part is the derivative of the third ln. This green part is the derivative of the cosine, and the orange part is the derivative of the cubic. And we multiply all the pieces together. All right, that's how the chain rule works. That concludes our lecture on the chain rule. Good luck.